We're back. My video timed out and I had done a bunch of things down here, and that's why I've got my highlighting. So anyway, we're gonna pick off where the video stopped. Okay, so 5 choose 3 and 5 choose 2 and 5 choose 3. So we are using Pascal's triangle to find the value of each sum, then identify the single combination which represents each sum. Okay, so 5 choose 2 is here, right? So that's 10. So that's equal to 10. 5 choose 3 is 10. Okay, so that's 20. 20 is also represented as 6 choose 3, right? So 6 choose 3. All right, so 3 choose 1, 3 choose 1 is 3. So this is 3 is n, r is 1, okay? Plus 3 choose 2, so n is 3, r is 2. N is 3, r is 2, that's 3. Okay, so that is 6. And we also have 6 as 4 choose 2, right? So 4 choose 2. And then 6 choose 5, 6 choose 5, 6 choose 5 is 6, and 6 choose 6 is 1, and that's 7, and 7 is also the combination of 7 choose 6. 7 choose 6. So what I had done in the video that timed out was to write the identity or pattern that Blaise Pascal discovered for the sums of combinations. So what I had said was, if you see these 5s as both the n values, you notice that you have one more in the n as an answer, right? So you went from 5s to one more to get 6, right? You went from 7s being identical to one more to get 3s and one more to get 4, and then you went from the same 6s and one more to get 7. And then I said, look at the second value, the greater r value, right? That was r equals 2, r equals 3. Well, the greater r value was what represented the answer. The answer's r value, and these had r values, but the greater r value was written in the answer. And these were the r values, but the greater r value was written in the answer. So in general, what did he say? He said that when these values were identical, okay, so when these values were identical, say they were n's, okay, when you were adding these combinations, you would always get one more than the original n value, so n plus 1. And then r would be the r value that was 1 greater than the original, right? So this would be r, this would be r minus 1, and then this would be r. That's how he wrote it, okay? So this is the Pascal's identity. Okay, like a formula, okay? So using the chart, write some equivalent combinations. So this is another way to understand the patterns that are evident in the triangle. So if we said we wanted equivalent combinations, right, it would mean that the combinations were equal to the same value, okay? So therefore, combinations that are equal to the same value or answer. All right. Okay, so I suggested that we pick this row in the previous video that cut out on me. because it's got a lot of values that we can compare. Okay, so what I had said was look at the symmetry of these. So you could say that 6 choose 0 is equal to 1, okay? But so is 6 choose 6, right? Another observation would be 6 choose 1 is equal to 6, but so is 6 choose 5. So 6 choose 1 is equal to 6, but so is 6 choose 5, right? And then using symmetry again, 6 choose 2 is equal to 15, but so is 6 choose 4. So you can see that for every new column that we go in towards the center, right, represents another equivalent combination. So let's do the next one. So 15, and then this one. So 6 choose 3 was equal to 20, and I mean, there's not much to say, but I mean, it was equal to itself, right? So suggest a rule for finding equivalent. So these are equivalent, right? Because they're equal to each other. These are equivalent, equal, right? And these are equal because they have the same, they represent the same value, right? These are equal. So the question is, why or how are they equal, right? So look at them. So they have the same value here. They have the same n value, 0 and 6, right? They have the same n value of 6, 1, 5. They have the same value of n equals 6, and our values are 2, 4. So you take a second and you go, oh, okay. So if we have for every combination that has the same n value, okay, R1 plus R2 has to be equal to n, okay, where R1 equals the R in the first, in the first combination, and R2 equals R in the second combination. So what do I mean? So I mean, if you want to know these values are equivalent, then you should be able to say, there's R1, oops, let's do this. This is n, right? So they're the same n's. So this is R1, and this is R2, okay? So R1 plus R2 is 0 plus 6 equals 6, which is the same as n, right? If this is R1 and this is R2, then R1 plus R2 is 1 plus 5 equals 6, which is n, right? That's what we're saying there, right? So if we had F using your rule in E, which is up here, right? Write a combination or expression, and the textbook uses this word expression, okay, that is equivalent to each of the following. So if we say that this is n, right, n, and we say that this is R1, we say that since R1 plus R2 is equal to n, we'd sub in R1 of 5. We'd want to know what R2 is, and N is 12. Okay, so what's R2? Well, R2 is 12 minus 5 to give us 7. So 12 choose 5 is equal to 12 choose 7, right? And if we wanted to, we could really evaluate that and check that, okay? Okay, so this is N, this is R1, right? So 27 choose 0. So we have, since R1 plus R2 have to equal to N, then we sub in R1, which is 0. R2 we don't know. 27 is the N value, right? So then that means that R2 is 27 minus 0. R2 is 27. So R2 is now 27. So now we have 27 choose 27 is equivalent to 27 choose 0. Again, we could use our combination formula to evaluate that and that to check it, right? And then this one, what is this equal to? Well, since we know that N is 77 and R1 is 77, and since R1 plus R2, which we found up here, okay, is equal to N, we can sub in the R1, which is 77, and R2, which we don't know, and N is 77. So R2 is equal to 77 minus 77. So R2 is equal to 0. So then that 77 choose 77 is equal to 77 choose 0. Again, we could evaluate that using our combination formula, and that value would be equal to this value.